Section 2 covers elements of design. You can find elements of design for horizontal and superelevation in the Engineering Policy Guide, Category 200, Geometrics. 230 is alignments of the roadway, and 230.1 specifically horizontal alignments. More information on elements of design can be found on the AASHTO Green Book Chapter 3. For this class, we are using the AASHTO Green Book 2001 version. You may use a newer version if you wish, but the tables and the exhibits and page numbers may be a little different than what we call on the manual. Elements of design. A roadway design should provide safe, continuous operation at a speed at which most of the traffic travels under normal conditions while being economically practical. Geometric elements allow the designer to provide such a balanced design. These geometric elements are known as horizontal and vertical alignments. So what is horizontal alignment? Horizontal alignment is the physical location of a roadway baseline composed of geometric elements such as points, lines, and curves. This horizontal alignment is also known as a chain. Users can create these elements using GeoPack traditional coordinate geometry, or COGO, graphical COGO, or any of the horizontal alignment tools found within the GeoPack suite. Chains are expressed in terms of bearings, distances, curvature, transitions, stations, and offsets. Typically, the alignment dimensions and distances are tabulated in a manner that facilitates construction staking as conducted by a field surveying crew. Coordinate geometry definitions. Curves are a segment of a circular arc. We have 4 types of curves we can utilize in our designs: simple, spirals, reversed, and compound curves. Simple curves are most commonly used in highway design. MoDOT uses simple curves unless project parameters meet the requirements for a spiral curve combination. Reverse curves are only suitable for low-speed roads such as a temporary bypass. Compound curves are typically used for low-speed turning roadways at intersections. Spiral curves provide a gradual change from the tangent section to the circular curve and vice versa. The advantages of spiral curves are: a properly designed transition curve will provide a natural and smooth path and will minimize encroachment on adjoining traffic. Transition curve lengths provide a suitable location for superelevation runoff length, which we will discuss later. Spirals facilitate a transition in width where widening of the pavement is needed. Appearance of highway is enhanced. A transition curve can avoid noticeable breaks in an alignment or kinks. Coordinate geometry definitions. Simple curves are defined by degree of curvature in the traditional U.S. unit system and by radius in the metric system. The degree of curvature is an arc definition or chord definition. The arc definition has a central angle subtended by an arc of 100 feet, while a chord definition has a center angle subtended by a chord of 100 feet. Arc definition is used for new alignments. Once in a while, you will find old plans that refer to a chord definition. Also, railroads are designed by chord definition. The simple curve geometry. Let's learn the different portions of a simple curve geometry. We have the PC, or point of curvature, the PT, or point of tangency. Where the two tangents intersect, we call the point of intersection. We have a central angle, a length of curve or curvature, degree of curvature, the radius of the curve, the chord length, and the tangent length. All these values can be found using specific formulas that were calculated from the geometry of the curvature and the arcs. We have also dB, which is the distance back, which is the distance or the direction back from the PC to the PI, and the direction ahead is defined as the direction from the PI to the PT. Note that specifically you will find chord definition formulas and arc definition formulas. You may assume that a curve has been designed using arc definition if you don't see any notes. Anything designed as a chord definition should have in parentheses chord defined, since it is not the norm. MODAC criteria for curves. Arc definition should be used for all new alignment. Chord definition only used when an existing curve is utilized in the alignment and you're not changing any of the alignment. The approximate length of curvature. For design speeds less than or equal to 60 miles per hour, you can approximate a length of 15 times the design speed. For design speeds greater than 60 miles per hour, you can assume length by taking 30 times the design speed. For small deflection angles for roadways with less than 400 vehicles per day, no curves are required for central angles of 1 degree or less. In this case, you can say that the curve can have a little kink. L must be at least 500 feet for a central angle of 5 degrees. Continuing on with elements of design and horizontal alignment. When do we use spiral curve combinations? If project data meets all three of the following MODAC guidelines: ADT greater than 400, speed, design speed greater than 50 miles per hour, and radius less than 2,165 feet. When all those three are met, you need to use a spiral curve spiral combination. Let's study the spiral curve geometry. In a spiral curve spiral combination, which is the type of spiral curves that we use, we have the tangent to spiral point where the spiral begins. The next point is the spiral to curve point, curve to spiral, and finally spiral to tangent. The central curve is a simple curve, and the beginning and the ending curves are spirals, so you have an entry spiral and an exit spiral. So when we look at the geometry, we are more concerned with the overall PI of the tangents as they come through and intersect. And so that is considered the PI of the spiral curve spiral combination. And then the central angle of that intersection. Let's review the reverse curve geometry. So basically in a reverse curve, you have two simple curves back to back, kind of creating an S. So you will also hear it referred as an S curve. And basically they share one common point. The reverse curve starts with the point of tangency, the point of curvature, the PC, and the PT of that first curve is really the PC of the next curve, and so we call it the point of reverse curve. And then you end with the point of tangency, or PT. Typically, we design these reverse curves such a way that they're both the same curve geometry, so the same radius and the same delta angles, or central angles. You can use the different formulas shown below to find the different unknowns, so the offset distance and the tangent distance for the reverse curve geometry. Let's review the geometry of our compound curve. A compound curve is simply two different simple curves that join together at a common point. Each of the simple curves has a different radius and a different delta. You have a PC and a PT in a compound curve, and you have a point of compound curve where they join together. You also have a tangent 1 for the first curve and a tangent 2 for the second curve. The equation shown below can be used to calculate the different geometry. Chains are a combination of all the elements that we've reviewed up to this point, including points, curves, spirals, and other chains. Chains have stationing associated with them. Locations along a chain can be determined by the stationing. Sometimes station equations are used. So what are stations? Stations are simply points along a chain which describe a distance from a reference point, usually the beginning of the project. Conventional stationing proceeds north to south or west to east. One station is 100 feet in the English system and 1 kilometer in the metric. Finding station at critical points is pretty simple, as long as you know at least one point of beginning. So, to find the stationing points on a simple curve, you use the PI station is equal to the PC station plus the tangent length. To find the PT station, you take the PC station plus the length of the curve. In the SES combination curve, the SC station is the TS station plus the entry length of the spiral. The CS station is the SC station plus the length of the central curve. The ST station equals the CS station plus the exit length of spiral. Now for compound curves, the PCC station equals PC station plus the length of the first curve. And to find the PT station, you take the stationing at the point of compound curve plus the length of the second curve. Finally, for reverse curves, to calculate the PRC station, or the stationing of the point of reverse curve, you take the PC station plus the length of the first curve. To find the PT station, then, you take the point of reverse curve station and you add the length of the second curve. What do we place on our plans? So curve data for plans preparation should include the PI, PC, and PT stations, a central angle, a degree of curvature, a length of curvature, tangent length, radius of curve, superelevation, bearings, and overall PI for the SCS combinations. GeoPack will place many of these particular data. The top picture shows the common GeoPack plan preparation tags that you will find using specific tools. Gives you the total PI, the SC station, the CS station, and the total delta, the degree of curvature, and the length for the spiral as well as the central curve. It gives you the tangent for the spiral. It gives you the radius of the central curve and some other information. The MODET guidelines for stationing chains are as follows. The center line of median is generally used as the survey baseline for divided pavement improvements. If the median is greater than 100 feet or is not parallel, then you may consider to use the inside edge of the travel way of each lane for individual alignment. So for example, you'll have stationing for the southbound lane and one for the northbound lane. For undivided pavements, the survey baseline is at the center of the pavement. And I use quotations for center because, as we discussed previously in section 1, the survey baseline is not necessarily in the center of the pavement. We use existing center lines whenever practical, so we need to make sure that we involve the survey party early on so that we can get those existing center lines staked. The conventional station proceeds from north to south or west to east. Crossroad stationing of intersected roadways is based on the existing stationing if it exists. If there is no existing stationing on a crossroad, then stationing proceeds from left side of the intersection to the right side of the intersection. More guidelines for stationing chains. The new stationing for intersections is chosen such that a 5-station increment occurs at the intersection with the main roadway. For ramps, the baseline is located along the right edge of the travelway relative to the direction of traffic. Stationing for ramps is carried in the direction of traffic, except for a diamond interchange ramp. Diamond interchange ramps are stationed in the same direction as the main line, regardless of the direction of traffic. Ramp baselines are equated to the main roadway or crossroad at the termini. Regardless of the type of curve being designed, their design should be based on an appropriate relationship between design speed, curvature or radius, superelevation, and side friction or pavement friction. Now our discussion of superelevation begins. So what is superelevation? Superelevation is simply when we tilt a curve towards its inner side in order to keep vehicles from slipping due to the centrifugal forces acting upon them. A vehicle moving on a circular path experiences a centripetal acceleration, which acts towards the center of the curvature. This acceleration is prolonged either by the weight of the vehicle related to the superelevation, the side friction between the vehicle tires and pavement, or by a combination of the two. Some of the design's considerations for superelevation are as follows. The maximum superelevation rates are used to determine the minimum curvature for the design speed chosen. There are four factors that control the maximum superelevation rate that we select. 1. Climate condition, frequency and amounts of ice and snow. The terrain conditions, is it flat, rolling, or mountainous? The type of area, is it rural versus urban? Frequency of very slow moving vehicles. Certain limiting values for maximum superelevation rate, Emax, and side friction, Fmax, have been determined through extensive research and are used to determine the minimum radius of curve for a particular design speed. The limiting values for Emax and Fmax are found in Ashton Green Book. The equation below shows the relationship between the superelevation, the friction, and the radius of the curve. This equation is used to determine the values in the superelevation tables in the standard plans 203.20 and 203.21, as well as the Ashton Green Book superelevation tables. Transitioning superelevation. Transitioning refers to going from normal crown to Emax, as well as going from tangent section to curve and vice versa. The superelevation transition sections include a superelevation transition runoff and a superelevation tangent runout. The superelevation transition runoff is the length of roadway needed to accomplish the change in outside lane cross-slope from flat or zero cross-slope to full super and vice versa, while the superelevation tangent runout is the length of roadway needed to accomplish the change in outside lane cross-slope from normal crown to flat or zero cross-slope. Runoff calculations are calculated in several ways. For MoDOT designs, the runoff length is already calculated for specific lane widths in design superelevation rates. You can find them in the standard drawings 203.20 and 203.21, or the Ashton Green Book exhibit superelevation tables and graphs. The tangent runoff calculations can be determined by the amount of adverse cross slope to be removed at the rate at which it is removed. So you can use the formula below to find that tangent runout length, which is the normal crown slope divided by the maximum superelevation rate for that radius of curve times the length of runoff. Ashton recommends superelevation rates. 1. A maximum of 12% should be used for rural situations. Any superelevations greater than 8% should only be used where no ice or snow conditions exist. For urban design, you can choose anything between 4 and 6% maximum superelevation rates. Superelevation can be omitted completely on low-speed urban design areas. Because there is no single maximum superelevation rate that is universal, the transportation industry uses a range of superelevation rates for various criteria. At MoDOT, these superelevation rates are listed in the standard drawings 203.20 and 203.21. Ashton Green Book superelevation tables and graphs can also be used. As for MoDOT guidelines regarding superelevation, we use the superelevation rates found in the standard drawings. A maximum of 8% superelevation rate for rural design should be used, and only a maximum of 4% superelevation rate for urban design. So how do we actually find those values? You look up design speed columns and find the corresponding superelevation percent rate for the appropriate radius of your curve. You use the nearest value if not found in the table. There are three methods for attaining super on undivided highways, and these diagrams can be found in Standard Plan 203.20. Case number 1 is rotating about the center line, and you can see the diagram on page 3. Case number 2 is rotating about the inside edge of the pavement, and you can find the diagram on page 4. In case 3, we rotate about the outside edge of the pavement, and that diagram is shown on page 5. Super for divided highways, however, is attained by rotating the inside edge of pavement. How should you show superelevation on your plan sheet? Well, basically, when you are using the superelevation rates as specified on the tables without variation, you only need to show the superelevation maximum rate on your typical sections and any widening that is required. However, I can tell you that construction likes to see the station and superelevation transition slopes on the cross sections. They also like to see cross sections being cut at the transition point. So anytime where you're transitioning from normal crown to zero cross slope on the inside edge of the pavement to reverse crown and back to full super and vice versa, all those sections should be shown on the cross section just to help the construction inspector to find it easier when they are inspecting the project. So your section AA, BB, CC, and DD. If you are not using the superelevation rate specified in the guidelines, basically you, for whatever reason, constraints on the project, you've decided that you cannot go with the numbers on the tables and you variate from that, you need to provide complete details of all the transitions on the plans and probably a superelevation transition plan as well. Application of widening on curves. Basically, on the tables that show superelevation, you will also see a number for W, which is the widening that you need to add to the travelway, and usually we do add any widening on the inside of the curve, but we only do that when the lane width is narrower than the standard width as suggested per the guidelines. So if you have a facility that requires a 12-foot lane and you decide to design a 10-foot lane, more than likely you're going to need to add widening on the inside of the curve so that you can provide adequate width to fit the path of the vehicles entering or leaving the curve. The guidelines on widening according to AASHTO are as follow. On spiral curves, apply the widening to the inside edge of travelway only. On spiral curves, you may apply the widening to the inside edge of travelway, or you can divide it equally on either side of the center line. Widening should transition over the superelevation runoff length when practical, but shorter lengths are sometimes used. Widening transition should be a smooth, graceful curve. A tangent transition should be avoided. So how much widening do we apply on our roadways? Well, basically the amount of widening is based on the curve radius, the speed, the design vehicle, and the lane width. And like I mentioned earlier, the amount of widening is tabulated on MoDOT standard plans 203.20 and 203.21. These values are for a WB50 ASHTO designation design vehicle in a two-lane roadway. The WB50 design vehicle is an intermediate semi-trailer. Designers can always refer to the ASHTO Green Book for the widening tables.